Kia ora koutou, no mai, haere mai. Thanks for joining us tonight. I'm Natalie Newton from the Alumni Relations team at the University of Auckland. Welcome to Raising the Bar 2022. This is part of a global event series that brings research and education into city bars and now your homes. We're delighted that we're able to bring you this online event for the third time running, and we're looking forward to holding the in-person events in the city bars later this year. Over the next 6 weeks, top academics from the University of Auckland will be sharing their research and discoveries on a wide range of subjects, from democracy to wine to genetics. And we kick off the series tonight with a talk from Professor Andrew Schelling from the Faculty of Medical and Health Sciences. Andrew's talk is going to give us an insight into how much we can blame on our genes, whilst also explaining where advances are really being made in predicting common, complex diseases such as cancer. Joining Andrew tonight is our MC, Cherie Blenkeron, who has worked with Andrew for several years within obstetrics and gynecology, and now has a joint appointment in the Department of Molecular Medicine and Pathology and the Auckland Cancer Society Research Centre. Cherie is going to introduce Andrew in more detail and then lead the Q&A session with questions submitted by you, the audience. Now it's time to sit back and relax while I hand over to Cherie.
Kia ora koutou, ko Cherie Blenkeron toko ingoa. Thank you, Natalie, for the introduction, and welcome to the first session of Raising the Bar in Auckland, the home edition. I hope you're all comfortable at home. I'm just going to start with some housekeeping information for how to run the webinar. We're going to be taking some Q&A questions, so you can fill in any questions you've got for the speaker by clicking on the Q&A button at the bottom. That's now live, and you're more than welcome to ask questions as you go. We'll come back to those at the end. If you've got any questions that you really like the look of, you can upvote those as well. And so we'll pick the top rated questions to come back to at the end. So for today's Raising the Bar speaker, I'm delighted to introduce a long-term colleague, a mentor, and a friend of mine, Professor Andrew Schelling. Professor Schelling is the Associate Dean of Research at the Faculty of Medical and Health Sciences at the University of Auckland. He's the head of the Medical Genetics Research Group and is also the acting director of a recently formed Centre for Cancer Research. His research is primarily interested in understanding the molecular changes that occur and during the development of genetic disorders, with a particular interest on breast and gynecological cancer and reproductive disorders. And this is the work that I've been very lucky to be involved with for the last 12 years or so. His expertise in the field of genetics makes him the perfect candidate to bring you this discussion today on how genetics can, and as you'll hear, maybe can't be used for deciphering diseases. So I'd now like to welcome and hand over to your speaker today, Professor Andrew Schelling.
Thank you, Cherie, for that very kind introduction. Tēnā koutou, tēnā koutou, tēnā koutou katoa. Ko Andrew Schelling aho. It's a great privilege to be here. I'm a bit nervous to begin with and be the first speaker. I'm sure I'll relax as time goes on. So welcome to this presentation about the truth about genetic predisposition. Hopefully by the end of the talk, I'll give you a great appreciation of how genetic disease works and things to look out for. I guess I've been very fortunate. I've been involved in genetic research for the last 37 years. Yes, 37, I had to work it all out before, and I was surprised it was such a long time. 37 seems a large number of years. I've lived through the Human Genome Project that was allegedly from the year 1990 to 2003, but in effect, it was only actually completed last month. The last 8% took a number of years to be able to complete because it was so complex. Also had access to some very exciting new technology. Ability to sequence DNA using next generation sequencing has been outstanding in the last few years, and access to enormous computing power that's been necessary to be able to analyse genetics over the last little while. So in the last 30 years, we've seen some of the greatest advances in genetic disease study and research, and many of the most important genes have only been discovered just in the last few years. I'm going to talk to you today about genetic disease. And to me, that is something that runs in families. Things that run in families can be really significant, really big, really important, or they could be relatively minor. So there's a continuum, a spectrum of different types of genetic disease. I'm going to begin tonight's presentation by talking about some of the most important, some of the big, important, deadly diseases where we've been able to uncover some of the genes that have been involved in those diseases. And then I'm going to work my way down from the strong genetics to weak, sort of hard to soft. I don't know the best way of describing it. I just want to begin by talking about the fact that my wife hired a painter the other day to paint my daughter's bedroom. He said he was a painter, but apparently he wasn't. But his father was a painter. It would appear that being a painter is not inherited, he said, because he wasn't doing a very good job. About 20 years ago, I was involved in a project where I was looking at a family of women who had ovarian cancer. And over 3 or 4 generations, nearly every woman in each generation developed ovarian cancer at a very young age, and many of them died. And what we were able to do is look at that family and identify a gene that was mutated in the family and be able to help the following generations to make enormous difference in their lives and well-beings. So you can see that there is weak genetics and there's really hard genetics. And I'm just going to try and point that out to you over the next 30 minutes. Our DNA is made up of about 3.2 billion pieces of information that you could call letters of the alphabet. They're made up of A, C, G, T. And they code the 25,000 genes that we have in our genome. The genes make different proteins that make all the cells and our organs work in our body. If there's a spelling mistake somewhere along the way, and we know that we've got millions of spelling mistakes in our genome, some of them are relatively unimportant places, and some of them are smack bang in the middle of really important genes. And this the spelling mistake we often refer to as a variant, and if it's a really significant variant, we call it a mutation. But some of the variants aren't very significant, and they might only have a mild effect on disease. When I first began studying genetics, we understood very few diseases where there was a genetic component. And over the last few years, that number has increased. About the year 2000, we realized that we had been able to discover the genetic basis of about 1,000 different genetic diseases. And I just checked in the so-called Bible, which is called the Online Mendelian Inheritance in Men, and presumably women as well. It's always been called OMIM. I saw that there were 7,149 disorders where we had identified a gene. That's extraordinary. And there's been a rapid advance in the last few years. What we know is about 1 in 50 of us probably carry a significant genetic disease. Many of us will carry less significant genetic disease that may never see the light of day because the genes may be recessive in our genome and never make it to a disease status. But what we know is about 1 in 10 of those different genes that cause a disease, we can make a difference. And there's some sort of treatment that will either cure the disease or remove most of the impact. So I think it's really important and significant. So I'm going to begin just with some examples of some really important genetic diseases that have influenced the way we think about genetic disease over the last few years. So these often occur in areas such as neurology, cancer, heart disease, and a whole lot of other areas. We often refer to these as being monogenic, where just one gene causes the disorder. Probably the most important of these genetic diseases is Huntington's disease. This is a really significant disorder. It's neurological, and the gene for this was found in 1993, interestingly with a good friend of mine, Russell Snell, who's at the University of Auckland when he was spending time at the University of Cardiff in Wales. We all have a copy of the Huntington's gene, but some of us have a spelling mistake or a mutation in the Huntington's gene that causes this awful condition. What we see is progressive deterioration in people with symptoms developing in their 30s and 40s and progressive loss of control and early death. Just about everybody with a mutation will get the disease. There's no escape. And it's so the new technology, by looking at the type of mutations that have occurred, we can see that we can almost predict to the year or the age that the person's going to be when they actually develop the disease. At the moment, it's not curable, But we've got people working in the Faculty of Medical and Health Sciences in the Centre for Brain Research under the guidance of Sir Richard Fall, who are doing studies to try and find new treatments. Interestingly, they had to make their special sheep in Australia because our GMO laws in New Zealand didn't allow it to be done in New Zealand, and probably that should be about to change fairly soon. The condition that I've spent the most time looking at is inherited breast and ovarian cancer. So this is where we see that cancer runs in a family more than what you might expect. This is really tricky for something like breast cancer because breast cancer is really common. 1 in 8 or 1 in 9 New Zealand women will develop breast cancer. So it's not uncommon to have more than one family member with breast cancer, and it's got nothing to do with genetics. But this is where I'm talking about where multiple generations have breast cancer and sometimes associated with ovarian cancer. They often occur at a much younger age than what you might expect. They may have multiple cancers in the same person, so both breasts involved, or perhaps breasts and ovaries involved. Sometimes we see men are part of these conditions, and if a man is involved, does have breast cancer, he's probably got about 50% chance of being from a BRCA2 mutant family. So the two genes that are most strongly associated with inherited breast and ovarian cancer were found in the 90s, BRCA1 in 94 and BRCA2 in 95. And that was a time that I was working at the University of Oxford, and it was really exciting to see the development of these two different genes. Prior to the knowledge of these two genes, a lot of people knew that they're from a cancer family, and they would choose at a young age to have their breasts and their ovaries removed, regardless of not knowing what their genetic status was. After we were able to have these tests available, then women could get a test. So Angeline Jolly is probably the best example of this, a celebrity that was diagnosed with inherited breast and ovarian cancer. And she chose, rather than not undergo surveillance, she actually chose to have her breast removed first and then her ovaries removed later. And that virtually takes away all chance of the disease, not completely, but it does reduce it dramatically. About 1 in 400 of us is estimated are a carrier of this gene mutation. As I've already said, we all have the gene, it's just that some of us have a spelling mistake in the gene. In some populations, like the Ashkenazi Jews, 5% of their community actually have a mutation in the BRCA1 or BRCA2 genes. But because there's a treatment, which is rather radical, but it saves lives, then this has been acceptable to a lot of populations and has led to a lot of unnecessary suffering and early death. I used to do all the BRCA1 and 2 gene testing in New Zealand a few years ago, and we were able to have impact in a large number of people's lives. Likewise, I also used to do the genetic testing for inherited cardiac disorders, and one family I will never forget where we were able to make a difference in their lives. A young man died unexpectedly on a sports ground. He was only very young, and we were able to ascertain that he probably was a good candidate for this condition, an inherited cardiac disorder. And we were able to get hold of his DNA through the fact that he had a Guthrie card stored, a blood prick that's taken at birth. We were able to get some DNA from that Guthrie card and analyze the DNA and find that he had a mutation. We were able to go back to the family because the family were concerned that the same thing would happen to the sister, that she might also die unexpectedly as well. We were able to tell the family that she was clear, she didn't have the same mutation, but the mum was a carrier of the same mutation. And she'd been feeling unwell at the time, and we were able to put her on a simple medication, beta blockers, that were able to change her life. So we were able in this situation to use the genetic information to make enormous difference to the well-being and long-term health of that family. Another really important disease in New Zealand has been that of gastric cancer. So one of my good friends and colleagues, Professor Parry Guilford from University of Otago, was involved in a study with a Maori family that had high very rates of gastric cancer and a type of breast cancer called lobular cancer. He was able to identify a gene called ECAT-herin that was mutated in these Maori families, and in collaboration with the families, they published a publication in the journal Nature. And of course, Stan Walker has highlighted this recently, that if you're diagnosed as being positive with a mutation in the ECAT-herin gene, then you are able to get surgery to remove your stomach. And while that's extremely uncomfortable and difficult to live with, at least that you're going to live a normal life for a period of time. So genetic testing for these big diseases are really, really life-changing. They're relatively precise. We can get a pretty good idea what's going to happen. It's not perfect. There are a few wrinkles along the way. Testing is now becoming really cheap. For a lot of these diseases, there's now potential for treatment. But there are ethical issues, as you can imagine. What age should we test other members of the family? Should children be tested? Is that information going to be damaging? I was involved with the Huntington's family many years ago, where that information to the children was damaging, and they just weren't able to accept it or understand what it meant for them at the time. There are also some other ways that we might consider treating some of these genetic diseases. My PhD many years ago was on gene therapy. So this is an idea that if you've got a defective or mutant gene, the traditional, so for example, diabetes, then you replace the defective gene, the defective protein, which is insulin, by injecting yourself every day. So why not inject a normal copy of the gene into your body and that way replace the defective gene? And the system that we used back then, many years ago, was using viruses to carry the gene into the person's body and insert the good DNA and replace the defective DNA. It sounds like a perfect solution. And when I completed my PhD, which was 25 years ago, I announced to the Nelson Evening Mail, which was where my parents, which was my hometown, that a major medical journal, of course, that this is going to be what everybody is doing in 5 years' time. Unfortunately, 25 years later, it's only just becoming common. There have been some deaths along the way where healthy people died as part of some of the medical experiments. The 3 that have died clearly from gene therapy experiments. So they've changed the type of virus that they've used, and it now seems to be some FDA-approved gene therapy studies, treatments that are now approved. We have had the ability for a number of years to look and remove embryos fetuses that are carriers of gene mutations through prenatal diagnostic testing. This was using things like amniotic fluid or a collection of chorionic villi samples, but this was always quite traumatic. And so if the baby was found to be a gene carrier, one outcome was to abort the baby. Another solution was to carry the baby but be prepared for the condition as it arrived. We now have the ability to do something called pre-implantation genetic diagnosis, where a couple would have to use IVF or in vitro fertilization. They'd have to create an embryo using the sperm and eggs, and then they would go through and check the embryos to see if it carried a genetic mutation for the disease they're trying to avoid, something like a BRCA1 mutation or Huntington's disease, and then only replace in the normal, the non-affected embryo and hope that was going to be okay. We now have a new technology called gene editing, a technique using a technique called CRISPR-Cas, where we now have the potential ability to go in and correct that gene mutation. This still isn't approved. There's a moratorium on it. It hasn't stopped people in China using the technology to gene edit embryos and babies. But most of the rest of the world, it is illegal to do that. He was arrested, locked up for a period of time. In New Zealand, we've got another interesting ethical issue around about ethnicity, and that is that most of the genetics that we use in our everyday life are based on European populations. We don't know clearly some of the genetic makeup of Maori and Pacific, and so our ability to diagnose genetic disease in Maori Pacific populations is a little bit more difficult than it should be. And all of us involved in medical research in Auckland and around New Zealand want to reduce inequities related to health. And clearly, this is a situation where genetics is actually making inequities potentially even worse. There's a really important project being undertaken by one of my colleagues, Professor Chris Print, who is leading a group, including Maori colleagues. It's called Rakiora, through Genomics Aotearoa, that's trying to address the genomic issues in our Maori Pacific folk, and that will help with reducing some inequities. Now, an interesting thing turned up a little while ago where I was sitting in my office on a Friday night, and I got a phone call from a woman in Australia who said, who was cold calling. She said, were you aware that New Zealand was out of step with the rest of the world, that insurance companies can use genetic testing information to either raise premiums or not take up a premium at all? And so a group of us have got together and written some newspaper articles and editorial to highlight this in New Zealand, that we're out of step. This is not fair. We don't think it should be like this, and we would like a ban on insurance companies using genetic testing as a way to influence premiums. I want to move now to the murky world, to the weaker genetics, where we look at certain diseases where we just see weak family history and enormous amounts of influence of environment. So we call this complex genetics, or multigenic, or multifactorial, or polygenic, a whole lot of different things. It's sort of the weaker end of genetics. For example, we know in many situations it's more than one gene and a whole lot of environmental influence. So a condition such as alcoholism, there may be certain genes that influence alcoholism, but what if I don't drink? That means that I'll never be exposed, that the environmental factors will never be exposed to the genetics that I have. In these situations, the spelling mistake is not enough to cause disease. It needs a whole lot of other genes to be involved to sort of all multiply various factors and some interaction with the environment. So this includes common diseases like cancer, heart disease, diabetes, inflammatory bowel disease. And the types of spelling mistakes we call them polymorphisms. I'm trying to keep as much technical language out of this talk as possible, but they're weak genetic effects. And we probably have 4 or 5 million each of these different little changes, and sometimes they are in genes and have some mild influence. So if one of these genes is involved, it's called an association. It's not causal. It predisposes you to disease, but doesn't guarantee that you're going to get the disease. And this is where it's become a little bit confusing. In some diseases, all these little tiny effects have all been joined together and used as what we call a polygenic risk score. And in some diseases, the accumulation of all these little tiny things can make a huge difference. So many common diseases have been studied in the last few years in a type of study that, again, this is the last, hopefully one of the last technical words I use, a genome-wide association study. And the best way I can explain this is that they throw an enormous net out through our genome to try and pick up all these tiny little factors. I quite like anchovies on my pizza. They make them taste really nice, but you're not going to get a meal out of a tiny fish like an anchovy. So anchovies on a pizza are great, but they don't make a meal. So likewise, these little tiny gene variants that are found in these complex diseases, the common diseases, are important. They're associated with the disease, but they're not causal. They don't make the disease happen. And this has led to a lot of confusion in the media and in the community. There's some really good examples of where it's made an enormously important contribution. For example, in breast cancer, I've already talked to you about some of the really big genes, but when you accumulate some of the really tiny little gene factors, they actually make up about 18% of the component of breast cancer. They're all helpful, but they're not terribly predictive. I worked on Crohn's disease several years ago, which is an autoimmune disease. It's thought to have arisen due to the hygiene hypothesis. 100 years ago, some of these autoimmune diseases didn't exist, but we've become really clean since then. And some of these conditions are where the body is starting to fight against itself, and probably Crohn's disease fits into that paradigm. When I first started working on Crohn's disease, there was one gene associated with the condition. Using these fishing types studies, the Genome-Wide Association studies, or GWAS, we now have about 200 different genes that have been associated with the development of Crohn's disease. And some of these completely opened up new avenues of investigation. the idea that bacteria in our gut could interact with our DNA and lead to the development of Crohn's disease wasn't really thought of. A molecular process called autophagy, which is the way that cells devour each other, was also found to be involved. So by using these types of genetic studies, association studies, we'll be able to identify a large number of new genes that had never been thought of as being important and involved, and opened up new possibilities for understanding knowledge and potentially new treatments. For obesity, we know that if you have two obese parents, you've got an 80% chance of having an obese child, whereas with normal weight parents, only about 10% chance of having an obese child. So we know that genetics plays a large component of it. There are some really big genes that are involved in obesity, but there's some everyday genes that also are important. There's one called FTO that was identified several years ago that probably makes about 3 kilos worth of difference to our body weight. An interesting one has been the CREB-RF gene, which is unique to our part of the world, which has only been found in Murray Pacific individuals, and it makes about 5 kilos worth of difference if you have the right genes. Originally, it was called an obesity gene, but now we think it actually might be related to lean body mass. So by having this gene, you actually are bigger and stronger, and that may be the case in our Murray Pacific community. I realise I'm running a little bit short of time, so I'm going to just speed up. I'm just going to skip over a few things. We now move into the world of lifestyle genetics, a very murky world. So a lot of the things I've talked about today have been from hard genetics to soft genetics, but they've all been valuable. But there's a whole lot of other things, traits like, but not necessarily disease, things like baldness, food preference, freckles, addiction, that now we have genes have been associated with this, and companies have been going direct to consumers, and people are able to spit into a tube and get information about these genes. I discovered that there was a gene, a condition called fear of public speaking, and 802 genes have been associated with. I've probably got most of them working right at the moment. And so some of these associations are interesting, but not terribly important. It often used in these types of genetic testing to target the worried well. They've been often poorly communicated what they mean through the media and especially through social media. One of the controversial ones that's popped up over the last few years is the gay gene. I don't mind if there's a gay gene or not a gay gene, but people have gone looking for it. And a recent study that came out just a few years ago, published in a really good journal, studying large numbers of people, found 5 hits. So there's no gay gene, but there's some weak associations. And the interesting biology behind these weak hits was that one of them was related to the sense of smell, and we know that attraction smell is important in that. And the other gene, one of the other associations found was that associated with male pattern baldness, which again speaks to some sort of hormone interaction. So there are some very controversial genes, and with some of the lifestyle genetics has been exploited by different companies that are going direct to consumers. I refer to this as genetic horoscopes. They may be interesting, they may be real, not always based on robust science. I can't believe there are 802 gene targets affecting fear of public speaking. I'm going to move now to the condition that was sort of highlighted in the abstract as part of this release, which is the age that you lose your virginity. So this, at face value, seems sensational. How could there be a gene that influenced your age at virginity? But if you really were to think about it, the age at puberty is a very well-defined event in people's lives. If we go back 200 years, people went through puberty age 18 or 19. Now they go, men and women, boys and girls go through puberty age 12 or 13. So there's clearly some factors at play there, probably related to good health, body weight, that allow puberty to happen earlier. Age at menopause is fixed. It hasn't changed for thousands of years. So what this study was really doing was they asked nearly 400,000 people about what age they lost their virginity, which is probably a marker for puberty. And they found some really significant and robust associations, very, very weak, but in that large number of patients, they were able to find a few hundred gene variants that seemed to be clearly associated with the age of losing your virginity. Some of those related to reproductive factors, hormone levels, for example, and some of the genes that they found were associated with behavioral and psychiatric traits such as risk-seeking behavior, ADHD, sociability. So some of the things they found sound really interesting to an academic like me, but aren't terribly important. They're not diagnostic. They're not going to be useful. You will never be able to predict reliably the age that you're going to lose your virginity by doing a gene test. It's just fun and interesting. Let's still finish by turning everything upside down on its head and just give you two last examples about nature versus nurture. I read in the notable medical journal, the Herald, several years ago, that if you have both parents that smoke, you've got a 25% chance of smoking yourself. If only one parent smokes, only 11% chance. If no parent smokes, only 4%. So doesn't that make you think, oh my goodness, you just copy what your parents do, and that familial influence dictates your behaviour. Surely this lands firmly in the area of nurture. However, since that notable article in the New Zealand Herald, gene variants have been found in a gene called CYP2A6 that related to nicotine metabolism, and it seems very clear that some individuals, based on their genetics, find cigarette smoking much more enjoyable and find it a lot harder to give up. So I would argue that underlying in that study, even though it looks like it's all nurture, there is always going to be a genetic influence. And I guess my final example of how genetics sometimes is overhyped is a very interesting study done a few years ago, looking at Japanese that moved to Hawaii. And what they found is in first generation and second generation, a doubling in breast cancer. And for stomach cancer, they saw the exact opposite, a halving and then a halving. So you can't argue that genetics is at play in that example, because genetics doesn't change in 1 or 2 generations. And this probably does always show that it's always influence of environment. So we know that changing diet, moving away from a soy-based diet for the Japanese, the role of phytoestrogens that seem to be protective against breast cancer. And in stomach cancer, the possibility of H. pylori, a bacteria in the stomach, may reduce as they move to a different country. So I hope that I've explained something today about the importance of genetic research. It really, and genetic testing, it has really led to life-changing information. I also want to point out how involved the University of Auckland has been in some of this research. Many of us have been international partners in many of these types of studies, and we're able to continue some of this research here in Auckland. We've got access to some of the best technology in the world, and some of the best people are here. We don't always have enough research funding to do everything that we'd like, but we do a pretty good job here. We're really and truly punching above our weight. And we really need to consider, we need to use this information to reduce the inequities in our health system, especially to Marion Pacific, to make a difference, to make sure that they always have access to this technology. So I hope that I've shown you today in a very short period of time that some of the genetics is really exciting. It's been life-changing. Some of the access to genetic testing is really important. We can really help people and families where disease does run in families. But there's other genetics at the other end. It's a little bit fluffy, and sometimes we just need to take them with a grain of salt. And a lot of them aren't diagnostic or prognostic. So thank you for listening. And I see some really good questions coming up. But I'm just going to take a break there and hand back to Cherie.
Great, thanks, Andrew. Some really great questions coming through. If anyone's got more, I'm looking over the other side, that's why I'm looking there. If anyone's got more questions, please add, because they're great and they're giving me lots of ideas to grill Andrew. This is the time I get my own back. In 2012, I inherited a lecture from you, Andrew, and you introduced me to the lifestyle genetics testing company 23andMe. And this might be a company that a lot of people are aware of, that offers you sort of rub your cheeks and you spit in a tube and then you send it to America. And they will do looking for these little variants in your DNA, and then they send you a report back. And there's some interesting things, and you might be also familiar with Ancestry.com. They also offer this, so they tell you where you're from in the world. And so I had my test done in 2012 because of your lecture, Andrew, because I thought it would be an interesting talking point for the students. And my Ancestry.com or my Ancestry version is really quite boring because I'm 100% European. There's some interesting traits that they now bring through. And I looked at it this morning and it was horrifying actually how good some of them were in predictions. So it was updated, and some of the gems I picked out were, and you'll notice, like Andrew mentioned, these aren't predictive. These are, they're not diagnostic or reliable. They give you a hint, or I think of these variants as little sort of dimmer switches. So one of the things was I'm more likely to have misophonia, so hating chewing sounds, and that is evident every night in my house, so that's true. I'm likely to at least have a little unibrow, which I thought was rather insulting. I'm likely to wake up at around 7:48 a.m. precisely, which I thought was very odd. Likely to be bitten more often by mosquitoes and others, which I can confirm is very true. So all these absolute gems, but they also, along with these traits, they offer the ancestry information. And you can also in America get slightly more concerning information, such as carrier status for genes such as BRCA1 and 2. So do you want to, because people might be familiar with these tests, these Ancestry.com, 23andMe, do you want to comment on those a little bit, Andrew?
Yeah, I mean, they're not terribly helpful. It's horoscopes. Yeah, the monobrow thing's really interesting, isn't it? Perhaps you could just look in the mirror and work out whether you've got a monobrow rather than predisposed to getting one. I mean, my 96-year-old mother had a DNA test which was looking for ancestry type things, but that data is also going to be stored somewhere, and there is some concern about genetic privacy and some of the value of that information. And I mean, people are allowed to have fun, that's okay, but what if you hear that you've got low risk of breast cancer and you might have a BRCA gene mutation, for we know? If you get told that you've got a low risk of breast cancer through one of these lifestyle genetic horoscopes and you stop getting your mammograms, I think that's criminal. And we also don't know if having one of these lifestyle tests also means that you influence your insurance, and whether or not the insurance companies are allowed to have a look at that information and set their premiums based on this weak genetic information. It's interesting, and I shouldn't stop anybody doing it, but I've always been on the other end of the spectrum, thinking it's not terribly important.
Yeah, it's quite fun, but take with a pinch of salt. They do on the webpage have a lot of good information about talk to somebody to help interpret your data, but it's so convenient. Why would you? You kind of get the test. Yeah. So leading on from that, one of the questions I had, and you brought it up, was about sending your DNA somewhere. And I have a sort of ethical, theoretical question. I've got two questions, and I'm going to spring these out. Who owns your DNA, and who owns the data generated from your DNA? I would, if I was asked that question, I'd ask your opinion, because that's something you're very good at. I mean, I think as an individual, I should be owning my genetic information. And I think with a lot of work done in New Zealand recently, Maori data sovereignty, and also data management type systems, where we have to be very careful
how we share that information, who has rights to it. Can we withdraw that information at any time? I think there are a lot of considerations that we need to take into account. And increasingly, whether or not we should be doing all the genetic testing in New Zealand. At the moment, nearly all our genetic testing is sent offshore, which is fine, but maybe fine, but the only way of getting that information. But who's going to hold on to that data, and what some will they respect Maori Pacific genomes? We're not sure, and so we need to have really robust systems in place to make sure that our genetic data is protected at all time.
Great, thanks, Andrew. I think we should move on to the questions, because we've got quite a few good questions. You're able to see them as well, I hope.
So I've got the top one, which from Anonymous says, research so far suggests demonstrate genetics cause personality disorders. I don't think they do cause personality disorders. They're associated with them. We know that a number of those personality disorders are traits, and there has to be some genetics involved. But you could never diagnose one of those disorders based on the genetics. I didn't have time to go into some of the other genes that have been interesting recently. The warrior gene in New Zealand caused quite a stir in our Maori Pacific community, which was associated with in the Maori community and led to a lot of devastating. It was very poorly done, poor research, and the way it was presented was inaccurate. Really good question from Dan. That's probably above my pay grade. It's great that you're doing this through Starship. They're a really interesting collection of different types of cancer. Is there any correlation between any of them? Is it purely by chance? I'm not sure. I think you've got to keep on pushing and find out as much as you can. I had somebody email me who I first talked to about 20 years ago, who finally got a diagnosis. They couldn't find a mutation in a BRCA1 or BRCA2 gene, but they found a mutation just literally within the last month in another gene. So don't give up hope. Keep pushing, keep working with the people in the Starship. That's a rather interesting collection of cancer within your family, and I'm not knowledgeable enough to be able to make a diagnosis from that. And obviously the people in the Starship are far more smarter than me, haven't been able to either. Kia ora, Dan. Thank you for the question about gene therapy. That's so you take me back. So what you do is you put a gene for the normal part. So you've got a defective gene that makes a wonky protein. So you just put into the virus a normal copy of the gene and use that to infect the cell. And if it goes into the right place inside the cell, it will make its way into the nucleus and insert itself into one of the chromosomes somewhere. So it needs to go into the part of the body that is affected, and sometimes that can be quite a broad range. So getting the virus to infect all the parts of the body that you'd like it to is technically quite difficult. But if it was in like a kidney or something like that, then you may be able to get enough spread within that tissue to be able to replace the defective protein and for some sort of normality to come into place. So, I think there have been 2,000 gene therapy trials done over the last 20 years. Some of them have been very effective and some of them have not, but some of them have now been approved by the FDA. So I think we are going to, 25 years after finishing my PhD and saying it was going to become mainstream, it may be emerging as a new technology. There's another aspect of this, which is gene editing, which may also be used as part of gene therapy that may be more accurate. And the medical interventions I've spoken about today, I'm not sure which ones you mean, but the women in the breast cancer families have already seen their sisters, their mothers, sometimes their fathers die of cancer at a very early age. So to undergo surveillance, which is sort of watching and waiting, may be an option for them, waiting for a mammogram to turn up to be positive. But ultimately to have surgery, it is life-saving, and these aren't normal people. They're not people like you and I that have never faced significant death and misfortune in their family. So they do make decisions that some of us would find slightly slightly strange or unacceptable, but they really are life-changing. If you're talking about some of the other technologies like pre-implantation genetic diagnosis to remove abnormal embryos, do I support that? I think there's a place for that. In New Zealand, they have funding to do a certain number of those PGD, pre-implantation genetic diagnosis type things. It has to be for a significant or a disease that's serious. However, it's not always clear to me what is serious in the New Zealand context. I was approached once by a couple who had an eyelid disorder. And I'll say the name, blepharophimosis ptosis epicanthus inversus syndrome, which leads to a slightly unusual eyelid, which can be corrected by surgery, and they wanted to use PGD for that, and I didn't think that was acceptable. It wasn't serious enough. So some of that technology can be of great benefit, and mean that families don't live in dread that their newborn baby is going to carry the disease that's been running in their family.
Andrew, I'm just looking at the upvoted questions. There's a few questions on epigenetics and whether you can change genetic outcomes by changing your environment.
Yeah, I'm not great on epigenetics, as Sri knows. I mean, it's important, but it's been very hard to measure, very hard to treat, and probably some of my colleagues are probably about to wring my neck. But I mean, epigenetics is important. Our diet, our behaviour, all the things around us can affect gene function, and the microbiome I know is really important as well. There are many other factors that I didn't have time to talk about today. I actually had microbiome and epigenetics as things I didn't have time to talk about today. So yes, really important, very hard to measure. Epigenetics influences, very hard to treat, but probably really important. Clearly, diet is a major factor in our health and well-being, and all these diseases that there's an epigenetic factor. It's just been very hard to measure. What question should I move on to next?
So it sort of links to the question of nature or nurture. I suppose epigenetics is the idea of changing something that you can inherit, either inheriting your individual cells, inheriting it from one another, or you inherit through the family. For me, I think of the nurture as being quite regulating of epigenetics, if you have an inherited component. So there's a question on, in your opinion, is nature or nurture stronger?
I say genetics is both underhyped and overhyped. Genetics is always important. It's always there. The example I used about smoking in families, you'd think that would be the most extreme nurture type event, but there's always genetics at play. But it can't be. Sometimes I think we perhaps overhype genetics, and sometimes we don't hype it enough. In some of those serious cancers, 5 to 10% of all cancers is genetic, and we need to pay attention to that. Why don't more people get gene testing done? It's a really, really significant way. One of the most powerful medical tools is our family history. And if there's disease that runs in the family, having a gene test and the thousands of genes that we now know, it can be completely life-changing. So I'm unashamedly sometimes overhype genetics as being really important and believe in nature. But some of these other conditions we've been talking about, like being gay, or things like ADHD, which are clearly a mixture of both nature and nurture. There's a question here about ADHD, and I cut out a little bit I was going to talk about ADHD. So ADHD has always been considered a behavioural or related to food or screen time and that sort of thing. And there has been a genetic link identified with ADHD several years ago. And it was quite extraordinary, the response to that. It was published in the journal Lancet, and some of the media that followed that went from genes associated with ADHD to genes cause ADHD. So that immediately meant that, oh, we'll keep on feeding them Fanta. Doesn't matter if they have plenty of screen time. It's now a genetic condition, and because it's genetic, it's now medicalized. So there must be a treatment for it. There must be a drug for it. So these things are really difficult to actually communicate into the community. And don't we know about science communication over the last couple of years in New Zealand related to a little virus that's been plaguing us, that we do need to have very clear messaging and accurate things. There is a link between all those conditions that you describe, ADHD, autism, and dyslexia. When you see the genetic studies, there are genes that are in common, and they each have their own unique genes as well. So it does seem to be some interrelationships between those. Mother side of baldness, that's what I've always believed. It's maternally inherited, same as some other X-linked conditions, such as my son has got colour blindness, which didn't come from me, it came through his mother's side. So there's some interesting X-linked conditions that and so the baldness is all, I don't know, that I learned that years ago, and I don't know if it's still true.
I didn't know that. I've got one question that I'm curious about. Is it possible for the effects of one genetic mutation to trigger another genetic abnormality? I can only think of one example myself, and that's what we work on.
Yes, that's right. Yep. So that's, yeah. So people with BRCA mutations end up with mutations in their tumors, like P53. A really important gene. So yes, that is there are certain genes. Every time a cell divides, there's some spelling mistakes are made. Usually one spelling mistake every time a cell divides. In reality, there are thousands and thousands of spelling mistakes each time a cell divides. It's sort of like your spell checker on your Word program. And the spell checker goes through and corrects all the mistakes, but it doesn't get them all, and it often leaves one or two. If you have a mutation in the spell check, which are special genes that are involved in genome surveillance, such as BRCA1 and BRCA2 and a whole lot of others, then that increases the risk of gene mutations happening, and the cells go into the spiral of downhill spiral in terms of accumulation of mutation. So yes, the answer to that is yes. We do know about some genes that are really important for maintenance of the genome. Thank you, Greg, for that question. It was a statement more than a question. I didn't talk about my physical education past, but Greg was a big influence on me many years ago. So thanks for being along. You mentioned that a child of two obese, 80% chance of also becoming obese. If this is true, if this was still true, if the parents were of normal weight in their childhood but became obese in their 30s, 40s, well, I guess they'll be reproducing. Yeah, I think that. Yeah, so if they become, so that's a really interesting situation. If they become obese as they get older, clearly that's not genetics changing. So it may be environmental. That 80% chance of being obese, if you've got obese parents, is a mixture of nature and nurture. Clearly, your genes don't change as you get older. There might be some epigenetic changes, but in that case, if their parents were a normal weight in their childhood, you'd argue that was more nurture than nature. So you can have some fun discussions on this.
There's a question that's just snuck in at the bottom that I think is a curiosity, because it's something that someone we know close is very interested in, and it is, what about mitochondrial genes?
Oh, I didn't see that one.
It just snuck on.
Okay. Any sorts of criminal gene? Okay. What about mitochondrial genes? Again, it was one of the things like microbiomes and epigenetics. I didn't have time to talk. They are really important. Mitochondrial genes are a significant cause of disease, a number of different diseases associated with them. They're supposed to be maternally inherited. I saw an article today so that we need to rewrite our textbooks. They can be paternally inherited. Yes, mitochondria are really important. So another really interesting question. So there is a criminal gene, the monoamine oxidase, where an Italian judge gave somebody a reduced sentence because the genes made him do it. Insurance companies using genetic data to raise premiums? Is this happening? Yes. So that's absolutely, and I've launched a campaign about this. We didn't know this was happening. Insurance companies are allowed to use genetic information, genetic testing, to set their premiums, or decide not to give you a insurance policy at all. We're the only country like us that are still doing that. And I've had communication in the last week by a woman that had a BRCA gene mutation, her premiums were raised because, and the danger of this is that we've seen from international studies that when people are told that getting a gene test can affect their insurance, about 10 to 30% actually decline having a gene test done in the future. And we think that's really dangerous. The amount of extra information that insurance companies get from the gene test ahead of just knowing that they've got a family history isn't that great. But if it's meaning that people aren't getting life-saving genetic testing, I think that's really criminal. Question from Gemma: how do we get gene tested? If you suspected you had something running in your family, you can discuss that with your GP, and you get a referral to the regional genetic services that are based. There's some based here in Auckland, where you might get to see a genetic counsellor or a medical geneticist, and you could discuss your condition and your family setting, and they could discuss with you whether it's likely to be a genetic condition, what sort of gene tests are available, and what the implications might be for you. I'm sort of summarising an entire people's career in less than 30 seconds. So yes, it is possible to get genetic testing done easily in New Zealand.
I think we've got time for one more question if there's another one that looks of interest to you, Andrew.
They all look interesting, that's the problem.
Oh, I like this one at the bottom. What are the next frontiers for genetics?
Well, I think we're all going to get our genome sequenced probably at birth. And so that piece of that information will be stashed away, and unraveling what it all means that some of us are going to have to become gene coaches, where we're going to have to understand the interaction between our genetics and lifestyle and health and well-being. But it's inevitable that genetic information has become more and more important in the health environment, and has become an important component of what we're going to do in the future in terms of the medical system and our health and well-being. As we begin to understand more and more about our genomes and interactions with other systems, it's going to become more and more important.
Great, that's all we've got time for, Andrew. Thank you so much. A virtual round of applause, and unfortunately we're not propping up the bar, so we're not having a pint, but a virtual round of applause for Andrew. Thank you everybody for joining us today from wherever you are in the world. It's now approaching 9 p.m. in Auckland, and so it's time to close the session. We hope you've enjoyed the topic, and we've had some great questions, so it sparked some curiosity in all of you. So just to finish, Raising the Bar Home Edition is a series of 6 speakers over 6 weeks. Today was your first speaker, so you've got 5 more to come. And so we hope you can join us at one of the other talks that are coming up. To do this, you can just sign up using the link that was on the confirmation email that you received. And we'll also show the webpage at the end. So thank you so much, everybody, for joining us today. We hope to see you again soon. Ka te ano. Thank you, everybody.